Okay, well, welcome everyone to another TCS Plus talk. Today we're very lucky to have Divyarthi Mohan from Boston University, who's going to be talking about optimal stopping with interdependent values. Now, for those who are just maybe tuning in or watching online, TCS Plus is an online seminar series that tries to invite maybe general audience talks in theoretical computer science. So if you've seen there's some paper that you're excited about and you think would make a good TCS Plus talk, we're always soliciting suggestions and we're always happy to have people come and give a talk on our seminar. But with that being said, there will also be a small unrecorded session after the talk where we can ask questions and just like discuss further. But with all that, let me hand over the floor to Divyarthi and please take it away.
Thank you. Yeah, I'm really excited to be giving the talk on TCS Plus. I'll be talking about our work on optimal stopping with interdependent values. This is joint work with my really awesome co-authors, Simon Morris, who's at India in France, and Rebecca Reifenhofer, who's in University of Amsterdam. This appeared just this EC, so it's a pretty recent work, and you'll see that hopefully that it's very accessible. Like we are trying to introduce a new model, and so feel free to like ask me questions about it even during the talk as you fit. Cool. So let's start. So the very high level motivation about for this talk is on from online decision making. So in many of the scenarios, we need to be making our decisions online without knowing what's going to happen in the future, right? So let's say that I have this like tiny painting that I made for sale, and I want to sell this to the person with the highest bid, the person with the highest value. So I see someone who comes and says that I'm willing to pay $10 for it. And I think that, oh no, I think it's worth more, so I'm gonna reject their offer. So they are now out of the game. They are gone forever and I can't go back to them. And now the next person arrives and they're only willing to pay $6 now. And I think, okay, no, this is even worse. I don't want to accept this, so I'm gonna let them go as well. Now again, the third person comes and they are willing to pay $8. And maybe at this time, I think that, okay, maybe I really cannot do much more than this. Like I am like, I should probably just take this and like be happy with the value so far. So I accept them. But then it turns out if I had waited, I would have gotten an offer of $30, which would have been way higher and would have made me much more happy. So the main question here is that should we select the current option? Is it good enough? Or should we wait and gamble for something better in the future, right? And this is, of course, prevalent in like many, many scenarios, not just from like selling an item like an art or a house, but also when we want to hire a candidate. Do we want to accept the candidate that we have right now, who seems pretty good, but or should we wait for a better candidate in the future? Or when we the reverse when we are accepting job offer, like should we accept this exploding offer right now or should we wait for something better later? Or even like booking a flight, like is the deal good enough to book now or am I anticipating for the prices to go down? So in many of these scenarios, like we need good algorithms, like online algorithms that are able to make decisions without being certain about what's happening in the future. But in many scenarios, there are also an additional challenge present. For example, let's consider selling this item um, and think about having what your value for this item would be. Okay, let's say that I actually do have this painting for sale and think about how much you would be willing to pay for this, right? But now you might be wondering, this is some random doodle, like maybe it's like $5. Like why should I even care about this? But what if Eric knows that like this is actually a Picasso and like he tells you that this is a Picasso? Knowing this, I'm sure that for a lot of you, this changes what or like how you value this item, right? So we in many of these scenarios, we face these like partial information settings where like we don't even know our own values a priori because our values can depend on information that other people hold, right? Like we have these interdependencies in our values because our value for the item can depend on the information that all the people have. And this is prevalent in like really like across many different areas. Think about one thing I like to like have in mind concretely is the resale model. Like for example, think of selling this painting. So the information that you can think about is that like I not only care about how much I inherently like this painting, but knowing that other people really value this painting really increases the resale potential of the item, and that I need to take that into account usually when I think about how I assess the value for this item, right? But also, these sort of interdependencies and partial information are present in like other settings. For example, think about buying something from like online marketplaces, or like renting a house in Zillow. Like I don't have all the information I need about the house, or like I don't know exactly like if this is a good neighborhood, is there like good public transportation there? But maybe somebody who's more local knows whether like these informations and like that can like affect how I value this. Like or when I read reviews online for some items, that can shape how much I value this item, right? And so we want to take this like aspect of interdependencies and like partial information and ask how can we design good online algorithms in these settings. So the main question that we are going to be tackling today is like, given a sequence of n interdependent values arriving online, and upon arrival of each value, we have to make a decision whether we want to accept the current option and stop, or irrevocably reject and continue on to the next one. And the question is, how can we maximize the accepted value? Okay. And this sort of like optimal stoppings is where the title comes in. It has been studied a lot in like math and like computer science, about like having a sequence of n values, and like we need to be like choosing one value where at each after the arrival of each step, at each step, once you see a value, I need to decide whether I want to accept this or just reject and move on with the goal of maximizing the value. And so the reason why it's called the optimal stopping problem is because I want to figure out what is the optimal time to like stop and accept the current value we have, right? And it is pretty well known that without any additional information, no online algorithm can guarantee anything, right? Like, think about just seeing a sequence of ones so far, and like your algorithm is learning nothing. And depending on whatever your algorithm decides, maybe it won't be able to distinguish between in the future there's an infinity or in the future there is a zero, right? I need to be making these decisions online, and in like worst case arbitrary instances, I'm not able to like give any sort of guarantees because I can't distinguish between these sort of extremes. So there have been like many different ways to like tackle this by looking at reasonable assumptions in the information that we have, especially through the lens of like randomness and stochastic processes. So one is the profit setting, where the values V1 through Vn are actually drawn from some distributions. So each Vi is drawn from a distribution Di, and we know the distributions beforehand, even though we don't know what exact value realization we see. And you can think of like the values are arriving in some sort of worst case order or adversarial order before, and these orders are like decided before the realizations of the values. Okay. On the other hand, we have the secretary model, where the values can still be super arbitrary and like chosen adversarially, but the arrival order is going to be uniformly at random. So the instance has this nice like random structure introduced in the form of the random order of arrival. So in the profit setting, the arrival order can be worst case, but the values are drawn randomly from known prior distribution. And in the secretary model, the values can be completely arbitrary and adversarial, but the arrival order is going to be uniformly at random, right? And in both of these scenarios, there are like really nice, simple online algorithms that give you a constant approximation to the offline optimal. So if you compare against um, the expected value of the offline optimal of the profit who knows the realizations in advance and can always choose the maximum value, uh, we can get good online algorithms that compete with this expected offline optimal in both the profit and the secretary model. For example, in the profit setting, it's known that a simple threshold algorithm, that is, I'm just going to accept the first value that's at least half of the expected max, gives a half approximation or a two approximation to the optimal value. And in the secretary setting, knowing that like the arrival order is random, you kind of use the first few values as just a sample to kind of understand what the instance is, and then accept the best value. So far, this again gives you a constant approximation, an E approximation to the maximum value. Okay, cool. Oh, sorry. Yeah. And so this has been like super well studied. Like these are like really classic foundational results from like the 60s and like the 80s. And there's been a lot of work like building upon this to even more general, richer models with like combinatorial constraints and like multiple choices and stuff. But in a lot of but the main assumption here, and in all prior works that are like building upon this, is that the values are independent, right? Because when you allow for arbitrary correlation, there's pretty much nothing to guarantee here again. It's again the same sort of like hard instance where like no online algorithm can actually like do better than just like guess something at random. So there have been some special cases studied in the literature. For example, like thinking about like how much the dependency is like parameterizing the dependencies, but all of this kind of like has approximation ratios that like worsen with the correlation. So like the approximation ratio really depends on like how you parameterize the dependency. And moreover, like the notion of independent values is like really at odds with this interdependence that I was talking about. That, like, in many cases, I don't even know my value beforehand because I really need to know the information that other people have, and that's how that's what informs my value. So these information creates interdependencies between us, between our values. So, and this notion of interdependence is really at odds with all the independent value settings that have been like studied so far. So I think now I'll finally like explain formally like what I mean by interdependence and like what is the model of interdependence that we consider in our work. So the interdependent value model that we'll be looking at is like the celebrated model that was introduced by Milgrom and Weber in 82, building upon works of Wilson. And they won actually the 2020 Economics Nobel Prize in part for this contribution. So again, consider a single item setting with n agents, and each agent I has a signal Si. So this is their information, the private information they have about the item. So again, you can think of it as like just how much they like this item, or like knowing whether this is a Picasso or this is a Divya, right? And then they also have a valuation function VI that aggregates the information of all the agents into a value for the item. So this valuation function VI takes as input S1 through Sn, the signals of all the agents, and maps it to a value for the item for agent I. And you can think of the valuation function as like known and being monotone in all the agents signals. So this like simple model actually captures really a lot of rich settings. And for example, let's go back to the resale model that I was talking about earlier. So concretely, you can model like VI of S as being equal to my value for the item, how much like I inherently like it. That's the signal that I have, plus how much all the other agents would like it, like some weighted sum of like how other agents like the item, which captures the resale potential of the item. Okay. And so this model has been like really well studied in both the economics and um, computer science literature, especially in terms of like auction design. So you want to figure out how to allocate the item to n agents with interdependent values with the goal of allocating it to the agent with the highest value. So you want to maximize the social welfare. And in this auction design problem, you can think of the input to the auction as being the signals and the valuation functions, and you want to output a feasible allocation. That is, who gets the item, which agent gets the item, and come up with some truthful payments. I don't want you to worry too much about like truthfulness and stuff for now. I just wanted to say that like this was the one of the reasons for the why this model is so celebrated, because like these sort of auction design problems are like provide like really big challenges, even though they capture like really nice realistic instances. uh, it turns out that like there are like really strong impossibilities here compared to like classic auction design models. And this has been super well studied in both the economics and computer science literature. And there's been a lot of recent work in the econ CS, like computer science side, coming up with approximation guarantees under like more reasonable, nice valuation classes. This is just to like give you like an idea or like about or like the history of the model. But in our setting, we are going to be looking at this additional informational challenge or like a different informational challenge of online arrival, right? So this is going to be our formal model, like using the interdependent values um, model. So we are going to have a sequence of n agents with interdependent values arriving online. So again, each of the agents are going to have some private signal SI and some valuation function that maps the signals of all the agents to a value, right? So when agent I arrives, she is going to reveal her private signal SI. And to keep things really simple, we are going to start by thinking about completely non-strategic. So don't worry about truthfulness or worry about what would it mean. There is no strategic component. When an agent I arrives, she will reveal her true private signal SI. So that is our assumption. And then, but the valuation functions are all known beforehand and are public. And we study both the profit setting and the secretary setting in this interdependent values. So again, in the profit model, the signals are going to be drawn from some known prior distributions. So each signal SI comes from some distribution DI that's independently drawn. The distributions are independent of each other. So the signals SI are drawn from DI, and we know all of the distributions beforehand a priori. But the arrival order can be adversarial and is like fixed by some adversary beforehand, before the realization of the signals. And in the secretary setting, the signals can now be very arbitrary and adversarially chosen, but the arrival order is going to be uniformly at random. Okay. And in both of these, we again want to compete with the offline optimal. Can an online algorithm here do well compared to the expected max over all the interdependent values, knowing the signal realizations fully? Okay. Um, uh, yes. So one more thing is that like we will be focusing our attention on a class of general class of valuation functions called that are subadditive over signals. It is important to kind of focus our attention on specific classes of valuation functions, because without any assumptions, things are not going to be tractable. Like we will have very strong impossibility results and won't be able to provide any sort of approximation guarantees. So we will be looking at some class of valuation functions. Let me define what that is. It's actually a really general class of valuation functions that capture instances where the signals or the information are not complementary, are not complements of each other. So a valuation function V is subadditive over signals if for any subset of n, like n agents, if you look at the value when you evaluate on all the signals S1 through Sn. This value should be smaller than or equal to the sum when you evaluate V on the subset X and zero everybody else out, zero the signals of all the agents not in X, plus the value when you zero out the signals in X and only look at the signals in X complement. Okay, so valuation function is subadditive, is the value if you look at how V is the value of V on signals S1 through Sn, this has to be smaller than or equal to the value separately when you look at some signals only in X and signals not in X. Okay, is that clear? So this is a really big class of valuation functions. And in particular, it's a strictly larger class than the class of valuations called submodularity over signals, which capture which capture instances where the values like you get decreasing marginal increase in values like over the signals. Like the information does not give you increasing marginal utilities. And this was a very important class to get like approximation guarantees and interdependent auction design. And we will be focusing on subadditive over signals, which are like a strictly more general class of valuations. Okay. So yeah, so with that, again, this is our model. We are going to look at a sequence of agents who, after when each agent I comes, they will reveal their signal, private signal Si, but the valuation functions are known publicly, and we'll be considering both the profit and the secretary model. And actually, for the majority of the talk, I'm going to be focusing just on the profit setting. Um, but I'll try to say something a little bit about the secretary model at the end. Okay. So with that, yeah, and the valuation functions that we'll be like focusing on are going to be specifically subadditive over signals. With that, I'm going to start with some uh, bad news first. So even when we only consider valuations that are subadditive, in general, in the profit setting, no online algorithm can guarantee better than like omega n approximation. So there's like this really strong impossibility result that says that like anything, like the best thing that the online algorithm can do, like there's a worst case instance such that like the best thing the online algorithm can do is just guess something at random. There's nothing more to do. This is because the adversary can hide the most informative signal at the end. So recall that in the profit setting, even though we have these prior distributions, like we know the distributions from which the signals are arriving, the arrival order is going to be some worst case order, and the adversary can choose an order such that the most informative signal is actually at the end. And this is and I can prove this theorem in like just this one slide. So I want to spend like a minute to just show you the counter example. It's super simple. So think about the instance where the signal Sn, like the nth agent's signal, is going to be drawn uniformly from 0 to 1. And this is the only important signal. This is the only useful signal for anybody's valuation function. So you can think of every other signal S1 through Sn minus 1 as just being 0 or uniform 0, 1. We don't care. That's not going to play a role in our valuation functions. And every agent i's valuation function is now going to be equal to 2 to the I if the signal Sn is at least 1 minus 1 over 2 to the I, okay? Or 0 otherwise. So whenever signal Sn is at least 1 minus 1 over 2 to the I, my valuation function Vi is going to be equal to 2 to the I, and it's going to be 0 otherwise. So this means that for every I with probability exactly 1 over 2 to the I, it's going to be non-zero equal to 2 to the I. So the expected value for any given I is just 1, right? But note that like for any signal realization Sn, the true underlying values are going to look like something like geometric series of like 2. So there's going to be 2 square all the way to some power 2 to the k, and then it becomes 0 at some point and stays 0 because Sn is not big enough. But any online algorithm is only going to be seeing zeros, right? Even though the true underlying value looks like powers of 2 followed by zeros, because the most informative signal comes at the end and you don't see the realization up until the last buyer comes, we only see zeros. All that an online algorithm will see is just zeros up until the last stop, right? So the best thing that they can do, or like the only thing they can do, is just guess where to stop. But recall that no matter where I stop, my expected value is just going to be one. So the expected value of my algorithm is just one, right? No matter what the algorithm decides to do, says that I'm going to stop at some step I, the expected value of VI is just going to be one. So any online algorithm can't do uh, better than getting a value of one. But the optimal offline, the expected value of the optimal offline can actually be order n, because the offline optimal knows the highest 2 to the I for any given instance of Sn, right? So whenever sorry, this should be n. So whenever Sn is between 1 minus 1 over 2 to the I and 1 minus 1 over 2 to the I plus 1, 2 to the I is the biggest value in the sequence. So it will exactly choose 2 to the I. And this happens with probability 1 over 2 to the I plus 1. So when you sum everything up, we get roughly n over 2, right? So the optimal is actually going to be order n, but no online algorithm can get better than a 1. So there is this n factor gap. And we have this impossibility result. So to kind of like circumvent this impossibility result, or like have something more interesting to say, it's important to realize that like this instance has what we call far-sighted agents, right? So the agent's values can depend on the last agent, like they can depend on the signals of the future. So, and this makes sense in some settings, because maybe what you want to buy is like a long-term investment, and makes sense to think about what all the agents are how all the agents will informations they have. So it makes sense in like some model of like resale settings. But in many settings, you can think of the agents being myopic instead, right? Like their value of the item can only depend on the information that they see so far. So we can define that their value is only equal to S1 through Si, because that's all the information that they have. And this makes sense when you think of it as like the agent gets the item and like they get some utility and it's done. Or like you can even think of it as like it doesn't even make sense to think of some hypothetical like future agents. Like I got the item, I won the bid, that nobody else is arriving after the game ends. So what does it even mean to think about my value given the future signals? So in many settings, like you can think of that the agents having myopic valuation functions where their valuation is defined only on the signals that have arrived so far. Okay. So we make this distinction to look more closely at our online problems. And with this, we are able to get a constant approximation against the offline optimal when there are like myopic agents in the profit setting. Okay. And we will see later that like in fact we can also lose an additional factor of 2 and ensure that like the online algorithm can be truthfully implemented into a truthful mechanism and get an 8 approximation there. And interestingly, in the secretary setting, we don't need to make this distinction between farsighted and myopic, because the online arrival, like the random arrival order, really like gives us a good sort of like a snapshot of what the instance should look like, and we are able to like do well even without making this distinction between farsighted and myopic, and we get a constant approximation there anyway. Okay. Um, are there like any questions about the model and stuff before I um, go ahead with the results. Okay, good. So let's now see our like first positive result, which is that in the myopic setting, we have a simple online algorithm that gets you a 4 approximation to the offline optimal. Um, and this, when I say it's a simple algorithm, this is a simple, very simple online algorithm that kind of extends the classic profit algorithm of like the threshold algorithm. So we again, the theorem is that we are going to get a 4 approximation using an online algorithm compared to the expected optimal offline optimal. And note that because we are in the myopic setting, the expected optimal offline also only considers the myopic value of the agents, right? Because the agents' values always only depend on the signals so far. So our online algorithm is as follows. We are going to define a threshold which is equal to just, again, half of the optimal, expected optimal, exactly like how we would do in like the independent profit setting. But now, instead of just accepting the first agent that crosses the threshold, we do a second check before we accept. So we are going to accept an agent if and only if their value crosses the threshold x, which is equal to half of the opt, and it has to be the case that their value is greater than any future agent's value using the signal so far. So let's look at a pessimistic estimate of what the future agents values can be, right? Like given that the signals have been S1 through ST and zeroing out all the other, the future signals. So we know that VI's values at least this much. We have to ensure that like whenever we want to accept the current agent VT, their value is greater than the future, all future agents value using the information so far. That is, if someone in the future is obviously better. So if VI is going to be greater than VT when only evaluated on the signal so far, clearly with more signals, their value can only be higher, right? Like we have this monotonicity assumption. So it doesn't make any sense to accept the current value because I know there is someone who's better in the future. So I should just wait for them. So I'm just doing this like extra simple check where I check whether there is nobody better in the future using the current signals, along with making sure that I beat the threshold. Okay, so that is my algorithm. It's a simple threshold algorithm with this extra step that ensures that there is no agent who's obviously better in the future. Okay, and the proof idea actually, I think, is very simple. The what we want to do is to compare the value of the accepted agent BT to the value of the optimal agent of the instance, right? Like I want to compare these two quantities and I want to be able to say that like in expectation, VT is actually a good approximation to BI. So note that whenever the algorithm stops, or like, sorry, whenever the algorithm doesn't stop, this is because even the optimal agent does not cross the threshold. Because note that the agent whose value is truly the highest, like who has the highest value, they will always satisfy the second condition because their value is greater than everybody's value. So obviously it will be greater than their pessimistic estimate also, right? So the only reason why the optimal agent or like the best agent won't satisfy these conditions is because they don't beat the threshold. And if they don't beat the threshold, nobody else is going to beat the threshold because they have the highest value, right? So in instances where like, or in signal realizations where the best agent does not beat the threshold, the algorithm is not going to stop and won't accept anybody. On the other hand, whenever the algorithm stops, it has to stop at or before the best agent for the same reason. Because when you come to the best agent, and if you haven't stopped so far, and if the best agent is going to be able to satisfy both the conditions, I will stop right now and accept this agent. And if I don't, then the algorithm will never stop, right? So we are going to use these two observations along with the fact that our valuations are going to be subadditive. In particular, I'm going to upper bound the value of VI by the sum of VIs when I only look at the signals so far when I accept at time t, and the signals after uh, after we stop. Okay, so let t be the time we stop. So I'm going to use subadditivity to bound Vi as the sum of Vi when you only look at signals S1 through ST plus Vi when you look at signals after T. So ST plus 1 through Si. Okay. And for all of these three things, so the first one is just saying that the algorithm does not stop. And in that, I don't need to use, I just look at Vi as Vi. And the second term is like the algorithm stops and it's the Vi's value when I look at signals so far. And the third term is the algorithm stops and the Vi's value um, looking at the signals that have not yet been realized when we make the decision to stop. And I'm going to be bounding all these three different terms. And know that whenever the algorithm doesn't stop, we just said that nobody beats the threshold, including Vi. So I can just bound Vi with X. Okay, so I'm just going to upper bound the first term with the indicator that the algorithm doesn't stop times X. And whenever the algorithm stops, note that it has to be the case that the current value beats the future agent's value using the signals so far. In particular, Vt on S1 through St has to also beat Vi because remember, Vi, we haven't seen Vi yet and Vi is in the future. So it has to be the case that Vt of S1 through St beats Vi of S1 through St. And to bound the third, we cannot do this instance wise. We have to bound this in expectation. In particular, the main thing here that we are going to be using is the independence between uh, when we stop and the signals that we'll realize in the future afterwards, right? So the decisions that I make by time t are independent of the signals after t because the signals are all drawn from independent distributions. So the future signals are going to be independent of whatever decision I made if I stopped at time t. And using that, I'm able to like separate this the value of Vi and upper bound it very loosely by just the expected max, which we know is like equal to 2 times X because X is equal to 2 times X is equal to half of the expected max. So I'm just going to loosely upper bound this term by 2X. Okay. So we have that in expectation, the expected value of the max is going to be the sum of these three terms. That's what I've written here, and I'm just like separating the 2x term into like two times into two. Like I'm just separating 2x into x plus x. Note that this will just add up to x, which is half of opt, right? Like because this is the probability that I don't stop and this is the probability I stop, that adds up to 1. So I can combine these two to get x. And then the middle term is exactly the expected value of the algorithm because it's saying that whenever I stop, I get the accepted value in an expectation that's exactly the value of the algorithm by definition. So that is expected alg. And note that whenever I stop, the whatever I accept has to be condition on stopping will always beat X, right? So this is also going to be bounded by the expected value of the algorithm. Because whatever value I accept whenever I stop will always beat the threshold. So this is also going to be an expectation smaller than my algorithm's value. So putting these things together, we see that the expected value of the max is going to be x plus 2alg, where x is exactly half of the opt by definition. And this gives us our 4 approximation, right? Like the expected value of the opt is at most 4 times the alg, giving us our first positive theorem. Okay, good. Uh, any questions about this? Okay. So now I want to like spend a few minutes talking about the strategic case or like truthful mechanisms, because as I said, the interdependent values model comes from this like auction design um, framework. And recall that I said that the signals of I want you to think of it as like private information of the agent I, right? So a self-interested agent or a strategic agent may not reveal their true signal to the algorithm. Like we cannot take this for granted. So the question now becomes, not only can I make a good online algorithm, can I make it so that we incentivize them to reveal truthfully? So can we design a truthful mechanism, let's say with the use of payments, such that the agents are incentivized to reveal their signals truthfully, and I'm able to get a good approximation to compare to the offline optimal. Okay? And it turns out uh, you can believe me or like and it's a really nice like classic result in like independent settings auction theory, but also in the interdependent setting, that like to think about truthful mechanisms, it's enough to think about the allocation algorithm itself. So a mechanism can only be implemented truthfully if and only if the allocation that we give each agent I is monotone in its signal. Okay, so in other words, if an agent, uh, if agent I is going to be accepted at signal Si, when they increase their signal, they should continue to be accepted. Like it cannot be the case that when they increase their signal, we suddenly like stop accepting them. Okay, so given fixing everybody else, if agent I is accepted at signal Si, it has to be the case that they will continue to be accepted even if they increase their signal Si. And if this is true, we can come up with truthful payments, or like we can come up with a payment function that ensures that the agent has no incentive to lie about their value or like lie about their signal. And if this does not hold, actually we cannot get any truthful implementation of this algorithm. So let's look at our profit algorithm and see whether this is actually a truthful mechanism. So note that the first check that we do is a monotone check, right? If an agent beats the threshold, when you increase their signal, they'll continue to beat this threshold. So that is really great. But the second check is not monotone. This is not going to be truthful because when you increase the signal ST, it can be just because of how the valuation functions are, it can increase VI way more than it can increase VT. So for example, it could just be the case that like my valuation function does not even depend on my signal, but like someone in the future really cares about my signal and their values increases, right? So the second check is not a monotone condition. So the profit algorithm that we have is not going to be truthfully implementable. But it to circumvent this, we just turn towards randomness and say that like, well, okay, if you beat the threshold, then I'm just going to toss a coin with probability half its heads, and hence you will just get the item. I'm not going to check if there's anybody better in the future. We don't have to worry about that. And with probability half when it's tails, I will just go and see who has the best value in the future and then just give the item to them. That's it. I'm not even going to worry about anything else. So we are going to slightly modify the algorithm to just say that like, oh, let T be the first time that I beat the threshold. And with probability half, I just stop. That's it. And then with probability half, I'm rejected and you just go now use my signal ST to figure out who has the highest value in the future and assign it to them. And this makes the algorithm actually monotone, and hence we can come up with truthful payments. to implement this truthfully. Okay, so again, like putting these things together in the profit setting, even though we have like very strong impossibility results for the far-sighted case, in the myopic case, we can get a 4 approximation in the non-strategic setting. We can get an online algorithm that gets a 4 approximation to the optimal offline. And if you wanted to ensure that the algorithm can be truthfully implemented, we can get it with an 8 approximation. And maybe like I'll say one more thing about the secretary before I wrap up. We see that in the secretary setting, the expected value of the algorithm is going to be at least is going to be a 2-year approximation to the expected value of the optimal using a very simple online algorithm again. It's again, if people have seen the secretary problem before, you will know the classic algorithm, which is just skip the first N over E items and choose the best so far. So I'm going to do pretty much the same thing, but since we have interdependence, I have to talk about, I'm going to accept the best so far using the signal so far. Okay, so it might be that like knowing the realization of all the signals, this may not be the best, but I don't care about that. So I just skip the first N over reagents. I just use them as sample. And then I'm going to look at the first time t such that the value of the current agents using the signal so far is greater than all the past agents using the signal so far. And this is again going to give us a 2-way approximation. And the main idea here is basically the exploration phase or the sampling phase is not only giving us a good sneak peek at the underlying instance in terms of valuation functions, it also gives us a sneak peek uh, on what the actual values can be. In particular, subadditivity of valuation functions ensure that like when you look at a random set of signals and look at the expected value on this random subset, it's a good estimate on the full value on signals S1 through Sn, right? So because of subadditivity and the randomness of the arrival order, we have this really nice probability that like whenever I see like a partial value on a random subset of signals, that's a really good estimate of what actually this value would be when we know all the signals. And that helps us in like, and that helps us in like making this like second check. And the third thing is just like, I added this because like for people who know like secretary proofs, you would know that like this probability of like, oh, I haven't like accepted a suboptimal thing so far is like independent of like what the set is going to be. Like for any time t, there's a probability that uh, you have not stopped, which is equal to uh, the sample size over t. Like that's always going to be, and that's going to be true even here. And so using these ideas, we are able to show that like the secretary algorithm can get to a 2-way approximation, even in the far-sighted setting. Um, yeah, even in the far-sighted setting. So with that, I'll wrap up again. So we have these like nice results both in the profit and the secretary setting. One quick thing I want you to notice is that like our constants, if you see, match exactly the independent case except for losing a factor 2, right? Like so the best known or like the tight result for profits with independent values is 2, and the tight results for like a secretary problem without any interdependence is again E. So in our algorithms with interdependence are only losing an additional factor 2. And in fact, if the underlying instance just so happens to be non-interdependent, that is everybody's values just equal to their signal, for example, our algorithms will automatically recover the independent like tight results. It will become 2 and E respectively without doing any sort of additional checks. And if we want truthfulness, we lose an additional factor of 2. And actually, we have like more ongoing and like work recently to say that studies beyond this like simple like single choice like selection problem, and we show that like in the secretary model, the 2-year approximation actually extends beyond this single item case, like to online matching and online combinatorial auctions. So yeah, So with that, I'll stop. Like that's it from me. Like there are like really nice, interesting future directions here. For example, none of the results that we have are like tight. Like we don't know if like 2E is the right answer for secretary or like 4 is the right answer for profit. None of these are like right. So maybe getting tighter bounds would be something interesting. But I think the more interesting thing is that like online decision making and like online algorithms are like super like rich and well studied. So I think it makes a lot of sense to think about interdependent values in these settings, right? Like think about going beyond just the single choice settings with like combinatorial constraints like matroid constraints or choosing like k the top K options or like having online combinatorial auctions. It will be like interesting to know whether we can have good approximation guarantees even with interdependent values. Or like just think about other online stochastic problems that you like, and it will be nice to understand if interdependencies will be a challenge there, or like how can you like circumvent that. Yeah, thank you so much.
Okay. I guess we can either take questions now or we can also move on to the unrecorded session. Um, so are there any questions?
Maybe we can stop recording before.
Yeah, let's move to the